Assalamu alaikum wa rahmatullah. Today we'll discuss a new and interesting topic, which is taking derivative of matrices. Okay, this kind of high dimensional derivation has an important application in neural networks. Okay, so in many applications of neural networks, it is required to take the gradient with respect to a matrix, or let's say, in other words, we take the gradient or the derivative of a matrix with respect to vector or a matrix as well. We'll see that with some examples. Okay, this kind of derivative is called a tensor. Okay, so a tensor can be defined as a multi-dimensional derivative, which is usually more than two-dimensional derivatives. Okay, such entity collects the partial derivative in a higher dimensional format. Okay, so let's say that we have a matrix A. A belongs to R M cross N, and we want to take its derivative with respect to another matrix B, which is in the space of R P cross Q. Now, this derivative is a four-dimensional tensor. So it's a four-dimensional matrix whose dimensions are M cross N cross P cross Q. Okay, so the J has a four-dimensional form. Imagine it like this. Imagine it would be like a notebook which has pages. Each page is a M by N matrix. Okay, so in this case it has 4 pages. Each page have this M by N, let's say, matrix, for example. So if we want to index the elements of this derivative, we need 4 indices: I, J, K, and L, right? So IJ will reference the A matrix, and the QL will reference the B matrix. Okay, let's look at a simple example in figure 3.3. Okay, so we have this matrix 4x2 matrix, and we want to take its derivative with respect to a simple vector, three-dimensional vector. Okay, if we look at the figure 3.3, so this is our matrix here. This is our matrix, and we want to take its derivative. So let's say partial A with respect to partial X. Okay, so there's 2 ways to find this Jacobian, okay, which is the first order derivative. The first direct method, which is we take the derivative with respect to each element x1, x2, and x3. So the derivative of A with respect to x1 is a matrix. It's a 4x2 matrix. Then the derivative of A with respect to x2 is another 4x2 matrix. And similarly, the derivative of A with respect to x3 is a matrix, of course, a 4x2 matrix. So now we have 3 different matrices. We combine them, okay, as a notebook, let's say. So you have 3 pages. So now we get a 3-dimensional tensor. Okay, so the last, let's say here, let's zoom in a bit. Let's put it in red. This last dimension is the number of pages that we have in the tensor. This is one way to look at the tensor formulation. Another way is called flattening. So let's go to that example. It's here. Okay, so the thing is that we take this matrix A and we flatten it, so we convert it into a vector. Then we take the derivative of this flattened matrix, i.e. a vector, with respect to the vector x, which will give us a matrix. Now the matrix is 8 by 3. How we get the 8? The 8 here equals what? 4 times 2 equals 8, right? We have 3 elements of x, x1, x2, and x3, so we have 3 columns. Okay, so this is the flattened Jacobian. We need to reshape it into a 3-dimensional tensor, so it should be 4 by 2, which is the original matrix, and it has 3 pages, right? So we have 2 ways to do that. Okay, so let's look at an example, a general example, an important example here. So we have this mapping, which is a linear mapping here, right? It takes x from r(n) to r to the power m, right? The mapping is simple, so we get x is mapped to a times x, which is this form, the linear form, right? Of course, the matrix A belongs to the space r to the power m cross n. Now we want to take the derivative of f. Remember, f is a vectored valued function, right? So every element of f is a function of x. Remember, let's take the simple case, right? Let's say that n equals 2 and m is equal to as well, just for simplification, right? So here we have 2 elements, f1 and f2. This equals what? Matrix A11. Sorry about that. I think we need to zoom in a little bit, right? Let's zoom in. Okay, so here A12, A21, and A22 multiplied by the vector x1, x2, right? So f1, what does it equal? It equals, so this f1 equals this column or row multiplied by this column, right? And if we look at f2 here equals this row multiplied by this column. So f is a function of the rows of A. Okay, now we want to take the derivative of f with respect to A, right? So of course, since we have here m elements of f, so f has m components, we take each component, it will be the derivative of this component with respect to A. Okay, so this is actually belongs to 1 times m times n, which is actually, it's a long way of saying it is a matrix, right? It's an m by n matrix. Okay, fine. Now let's go here. So as we said before, the ith element of f is the ith row. So this is, say, the ith row of A, okay, times x, right? So as we said before, so if we want to take the derivative with respect to the elements of A, simply it will, okay, so the aij's are constants, right? So when you take the derivative of, let's say, 2x, the derivative is what? With respect, sorry, so this is aij, and you want to take the derivative with respect to aij. What is the derivative? It is x, right? So it's the same thing here. Okay, now this is a special case. As for the general case, if we want to take the derivative of the ith element of f with respect to the ith row of A, it will equal x transpose. Otherwise, it will equal 0 transpose. What does that mean? That's here, okay. I want to, let's say, take, in this case, let's say like this, I want to take the derivative of this with respect to a, let's say, another elements KL, right? So this is ij, this is a different variable. So when I'm taking the partial derivative of a different variable, this will equal 0. Sorry. This will equal simply 0. Now this you concatenate, you put the zeros beside each other, now we get this row vector 0 transpose, right? So in general, the derivative of the ith component is a matrix. So this, remember, this is 0, 0, and until the nth 0. So this is n, right? This again 0, 0 until you get here. Now at the ith, this is the ith column, ith row of the matrix. Here you will get x1, x2 until you get xn, and then you continue with the zeros, right? Like this. So this is a matrix in a sense. Okay, it's a two-dimensional matrix. Remember, this one does not count. Okay, fine. Now we have some useful identities that will help us in computing the gradient and the derivatives. If you have this dot product or inner product and you want to take the derivative with respect to x, it is A transpose. See, we take with respect to x, and A here does not have a transpose, now it becomes transposed. The same thing here, you take the derivative with respect to A, x becomes x transpose. Let's take this out, right? Okay, here it will become what? 2x. Think about this thing as x squared. You take the derivative of x squared, you get 2x, right? And as for this, okay, the derivative of ax with respect to x is a. Now this is a quadratic form, right? This is a quadratic form, a general form, right? So here, if you x transpose t, x transpose times p b plus b transpose x, if you take this with respect to x, you get this form. This is a general case. So let's say, okay, that we have this, let's call it matrix A, right? So we'd get here x transpose ax. If you get the derivative of this thing, you get what? 2x, sorry, this is x, this should be an x times a, right? Think about this thing, this is another quadratic form. Okay, so this is the general case, this is the special case that we usually deal with, right? And if you have a general quadratic form and you take the derivative with respect to the matrix x, you get a b transpose. Okay.